Deep learning has undeniably become one of the most important technologies of our time. This wouldn't have been possible without the great optimizers we rely on. There is considerable manual effort involved in researching and developing novel optimizers. Instead, we can shift our focus to automating the exploration of novel optimizers. But it comes with its own set of challenges. These challenges can be listed as follows: abundance of equivalent or suboptimal optimizers, optimizer representation, and hardware requirements. Currently, neural optimizer search is not open source. There is no benchmark, it has high computational cost, and it is not popular among researchers. NOSBench aims to address these challenges. It's open source, has a standardized search space, and offers fast evaluation with a simple meta-training task that can be trained in just 1 minute on modern hardware. Despite its speed, this task involves training a prior fitted network that leverages transformers. And transformers are one of the most popular building blocks used in many models, including ChatGPT. Additionally, NOSBench provides an equivalence check and a caching mechanism to further accelerate the evaluation process. Now, let's take a look at how our search space is structured. In NOSBench, we search for programs, where each program consists of series of instructions. Each instruction can be one of the following: a unary function, a binary function, or a ternary function. These instructions operate on a dynamic memory, using memory locations as both input and output. As you can see, within the memory, we have 9 read-only values. Some of these are essential for optimizers, while others can be utilized for joint hyperparameter optimization. Let's see it in action. In this example, our network has one parameter with a value of 0.5. And for simplicity, the gradient is always 0.25. First, we subtract the value in memory location 5 from memory location 3 and store the result in memory location 9. This represents the momentum hyperparameter. Second, we multiply the value in memory location 10 by the value in memory location 9 to calculate the momentum, and store the result back in memory location 10. Next, we add this momentum value to our gradient to calculate the update. Finally, we multiply this update value by the value in memory location 6, which in this case can be seen as the learning rate. With that, we proceed to the next step of the optimization. Let's see an example approach on randomly sampling from this search space. First, we sample a random number of functions. Next, we randomly select memory locations for both inputs and outputs. For the inputs, depending on the type of the function, we sample either 1, 2, or 3 inputs. Now, let's see how we hash optimizers for caching and equivalence check. Our proxy task involves minimizing a function using the optimizer we are hashing. Here, we plotted a simplified version of that function. To hash the optimizer, we calculate the exponential average of the loss at each step. Exponential average captures the positional information of the training. Finally, we take the hash of the final value to generate the optimizer's hash. While these concepts work in theory, let's see how they perform in practice. In this experiment, we compared various search methods for finding an optimizer within the NOSBench search space. The methods tested include random search, regularized evolution, and SMAC. We also benchmarked these methods against several well-known optimizers and the default training pipeline of prior fitted networks. Additionally, we created a search space for these optimizers and their respective hyperparameters to perform hyperparameter tuning with SMAC, establishing a baseline represented by the SMAC HPO line. Random search and SMAC outperform most optimizers but fail to identify an incumbent better than the default pipeline. The similar performance between SMAC and random search could be attributed to the sparse search space, as SMAC requires more time to effectively explore and exploit it. Both variants of regularized evolution performed exceptionally well. Notably, the ADAM-W variant, where the population was initialized with ADAM-W, succeeded in finding an incumbent that outperformed the pipeline, which we consider our main incumbent. Finally, SMAC HPO managed to outperform our incumbent. Let's see how well our incumbent generalizes to more challenging prior fitted network tasks. We tested our incumbent and the SMAC HPO baseline against the default pipelines of several models, TAP-PFN, PFNs for BO, and LC-PFN. While SMAC HPO struggled to generalize across these cases, our incumbent performed similarly to the best of the default pipelines for each model. In conclusion, NOSBench provides a systematic and efficient approach for comparing and contrasting various NOS methods. Our experiments demonstrated that the incumbent optimizer discovered using NOSBench performed effectively across a variety of PFN tasks that it wasn't originally optimized for. This highlights NOSBench's potential in identifying task-specific optimizers. For future work, possible action points include expanding to include more meta-training tasks, investigating joint and multi-objective optimization, comparing different hashing mechanisms and surrogate models, and hosting the benchmark on a server. Thank you.